I got requests to upload a lecture on the AK growth model, or the so-called Frankel-Romer model, as it is also known. This lecture is based on the two articles by Frankel from 1962 in the American Economic Review. He presented the AK growth model with an exogenous consumption side, so households have a given saving rate as in the solo model. And on the paper by Romer from 1986, where he basically introduces into this framework the dynamic optimization of the household as in the Ramsey-Koopmans framework. The presentation here follows again the textbook by Aguillon and Howitt, 2009, The Economics of Growth. Now the starting point is the following. We know already from the lectures on the solo model that the long-run economic growth rate is determined by technological progress. So physical capital accumulation on its own cannot explain long-run economic growth due to the decreasing marginal product of the production factor physical capital. However, we also talked about the Harrod-Domar model in another video, and this would imply long-run economic growth driven by physical capital accumulation if you assume away the diminishing marginal product of physical capital. However, such a model is inconsistent with the stylized facts of economic growth, and in addition, just assuming away the diminishing marginal product of capital is not really realistic. Now, the AK growth model somehow combines some of the features of the solo model and of the Harrod-Domar model by including technological progress of the learning by doing spillover type. And I will explain on the next few slides how this works. But mainly the idea behind it is that the use of physical capital in the production process itself increases productivity at the aggregate level of the economy. So that's learning by doing. You produce output by using physical capital, and that increases the productivity at the aggregate level because you learn how to produce better and so on and so forth. And this effect can lead to a situation where you can overcome the diminishing marginal product of physical capital. And in the following, I will first present the Frankel model with exogenous savings and then the Romer framework with endogenous saving. So first, we assume that there are J different firms, J running from 1 to uppercase N, and each firm J has access to a production technology of a Cobb-Douglas type, where output of the firm, lowercase yj, is a function of physical capital that the firm uses in production, that's lowercase kj to the power of alpha, and employment in the firm, lj to the power of 1 minus alpha. So that's the Cobb-Douglas part. And this is multiplied by aggregate productivity in the economy, A bar. And the crucial aspect of the model is now that this aggregate productivity, A bar, is determined by the learning by doing spillover effect, where the production of the different firms using physical capital raises productivity at the aggregate level. So this A bar is a function of some baseline productivity, A0, and the total use of aggregate capital in the economy, so the sum over the capital stocks of all firms from J equal to 1 to uppercase N of the capital used in all these firms. And the exponent of this sum over capital is eta, which measures the strength of the externality. So eta measures by how much the production with physical capital increases aggregate productivity. So it measures the strength of the learning by doing effect. So what we have here is a classical externality. The individual firm does not consider that its use of physical capital increases aggregate productivity, but the firm benefits if aggregate productivity increases. And these benefits are not internalized. So we have an externality, the learning by doing spillover. Now the next slide just clarifies some definitions, normalizations and assumptions. So for simplicity, we now normalize employment of a particular firm to 1 for all firms J, which makes life much easier and does not change any of the underlying results. Aggregate capital, as I already said on the previous slide, is the sum over the capital stocks of the individual firm from j equal to 1 to uppercase n. Aggregate output is the sum over all firms' output. And since these firms are similar, so they are not heterogeneous, there is symmetry, and the symmetry implies that the capital employed by each firm is the same. So capital J that one firm employs is just aggregate capital divided by the number of firms. Now we can compute aggregate output, aggregate production in the economy. And to this end, we plug the definitions that we had on the previous slide into the learning by doing spillover specification, which implies that then aggregate productivity, A bar, is given as this specification that we had previously, and now we plug in the capital stock of one firm, K over N, and since it's the sum of symmetric firms, we have the number of firms multiplied by the capital stock of each firm. And then of course, this N and this N, they cancel each other off, and we have that aggregate productivity is A0 times the aggregate capital stock in the economy to the power of the extent of the learning by doing spillover effects. Now we can plug aggregate productivity into the production function of the individual firm, so for this A bar here, and we make use of the symmetry result that we had on the previous slide to substitute out for capital of each firm, Kj, as uppercase K divided by N. So then we get individual output of one particular firm J, and if we aggregate over all firms by taking the sum over output of all firms, and since these firms are symmetric, we get the expression that we have here. So the number of firms multiplied by the expression that we have here, and then we can combine what we see here into this result, where k to the power of eta and k to the power of alpha, they combine to have k to the power of alpha plus eta. And this n to the power of alpha in the denominator, and this n here and this a, they can be combined to get the result that we have here, that this constant a would be a0 multiplied by the number of firms to the power of 1 minus alpha. Now we already see the crucial effects. So these learning by doing spillovers led to a situation where aggregate output is then a function of capital, but not only to the power of alpha, coming from the Cobb-Douglas production function and reflecting the diminishing marginal product of physical capital, but now including eta, the strength of the learning by doing spillovers. And as you can see, these learning by doing spillovers in principle could overcome the diminishing marginal product of physical capital. And here we have a parameter A, that's just a constant, but you already see why this is called the AK growth model, because it leads to a production function of the form A, a constant, times the capital stock. And we will elaborate on this later on. But first we specify the household side of the model. And first we do so according to the Frankel version of the model, where it's assumed that the economy is closed and no government is present, such that Y is equal to aggregate income and investment is equal to aggregate savings that we have in all closed economies without a government. But now the crucial assumption is that households save a constant fraction of income, whereas is the saving rate, so then aggregate saving would be uppercase S, and that's a fraction of aggregate income. The crucial assumption here is that S is an exogenous parameter, so that's the same as in the Solow model, so savings are not endogenized. Capital depreciates at the rate delta, that's the same as in the Solow model, so capital wears out at a given rate delta. And then we can specify the capital accumulation equation, where the change of the capital stock, that's net investment, is gross investment minus depreciation, again similar to the Solow model. And now we plug in aggregate income, that's from the previous slide, so that's this expression here. And that's different from the Solo model because we have eta in the exponent basically, and we don't have the Douglas specification because we normalized labor to 1. And now the growth rate of capital is the capital accumulation equation divided by k. We see then a lot drops out here, so k drops out here. Then here we get in the exponent alpha plus eta but minus 1, and we get the growth rate of capital on the left-hand side. Now what can happen in this economy? We consider 3 different cases, and the first one that we consider is the one where alpha plus eta is smaller than 1. So in this case, the learning by doing spillover effects would be comparatively weak. So they cannot compensate for the diminishing marginal product of physical capital, and that implies, intuitively it's already clear, that there will be no growth in the long run. Instead, the economy will converge to a steady state solution where capital accumulation ceases at some point. So we can set the capital accumulation equation equal to 0. So net investment at some point will be equal to 0 because we still have diminishing marginal product of the aggregate capital stock. If you solve this equation here for the steady state capital stock, then the steady state capital stock would be S times the productivity parameter A from here, divided by delta, because that's on the other side if we bring it there. And then to get rid of the exponent, we raise this to the power of 1 over alpha plus eta minus 1. And then we just swap numerator and denominator and multiply the exponent by minus 1. These two operations offset each other, and then we get the steady state capital stock for this case as a positive function of the saving rate and the negative function of the rate of depreciation as it is in the standard Solo model. So in this case we would have a steady state solution as in the Solo model. No long run economic growth is possible, and we would have convergence forces as in the Solo model. So if we start with a capital stock that is lower than the steady state, we would converge to the steady state from below, with the growth rate being positive. And if we start with a capital stock above the steady state capital stock, the capital stock would decrease and we would have a negative growth rate of the economy. Now the second case that we consider is when the learning by doing spillover effects are very strong. In this case the sum of alpha and eta would exceed 1, and in this case the spillover effects are so strong that they even overcompensate for the diminishing marginal product of physical capital. And of course, as is also intuitively clear, in this case you would have hyper-exponential growth. So you get an increase in output, and this increase in output leads to even more saving, and the more saving leads to even disproportional increase in output, and so on and so forth. So the growth rate would increase over time, so the growth rate would be hyper-exponential and explode. And this cannot be observed empirically, so this case is less relevant from a practical perspective. Finally, we come to the third case, which is the standard AK case. In this case, alpha plus eta would be exactly equal to 1. Now, of course, this is again a knife edge case because there is no reason whatsoever why eta should be exactly as high so as to ensure that the sum with alpha equals 1. In this case, the learning by doing spillover effects would exactly compensate for the diminishing marginal product of capital, and aggregate output becomes the expression A, this parameter, times the aggregate capital stock. So that's now the AK production function and the AK framework. And now you see there's no diminishing marginal product with respect to physical capital. The exponent here is equal to 1. And therefore perpetual growth becomes possible if k accumulates, because you see this here immediately. Whenever k increases, y increases also, because a is a constant. No diminishing marginal product kicks in. So then the growth rate of the economy can be solved by solving for the growth rate of physical capital from the physical capital accumulation equation. And there we already know that the growth rate of physical capital is S times A, so the saving rate times the productivity parameter here, minus the rate of depreciation. Now, this is similar to the growth rate of the Harold-Domar model that we had when you watch this video. However, in the Harold-Domar model, it was just present because it was assumed that there is no diminishing marginal product of physical capital. Here, the AK structure of the model follows endogenously from the specification that aggregate productivity, which can be thought of as technological progress or knowledge or whatever, accumulates due to the production process. So due to the use of capital in the production process, knowledge increases and that increases productivity. And it adjusts here exactly to the needed level for perpetual economic growth. So perpetual economic growth in this model becomes possible, although there is full employment of all production factors. If you look up the video on the Harold-Domar model, you know that there was the assumption that we had a Leontief production function, and it was not the case that we had full employment in equilibrium. So overall, we see that the AK growth model can overcome some of the problems that previous growth models had. It also generated perpetual economic growth in a kind of intuitive way by learning by doing spillover effects. But nevertheless, it was kind of displaced later on by the endogenous economic growth framework that actually modeled technological progress explicitly as the result of investment by firms to increase productivity. And so scientists then generate the stock of knowledge, and it's not just a byproduct of production. If you are interested in these endogenous growth models, which also Paul-Romer created in the 1990s basically, then there is also a video that you can find on my channel. However, now we also want to talk about the model when savings are determined endogenously. And this was the version of the model that was contributed by Paul-Romer in 1986. So there he introduces basically a Ramsey-Cass-Koopmans structure on the household side of the economy. So for this, he assumes an isoelastic utility function, which has the form that we have here, where consumption raises utility, but usually in a concave way for risk-averse households. And this is a standard utility function that you find in many economic models. If you are interested in it in more detail, there is a video that you can find on my channel on the isoelastic utility function and the different cases that can emerge. But this utility function describes the utility level of the households, and households now choose endogenously how much they want to save at each point in time. And that's basically the result of dynamic optimization that you can find in several of the videos that I've uploaded. I do not repeat all the steps here, but if you are interested in it, you can look up the videos on the Ramsey-Cass-Koopmans model or the videos on dynamic optimization in continuous time. Whichever of these you look up, you will see that the result of a dynamic optimization problem with this utility function and the standard dynamic budget constraint is the standard consumption Euler equation that we now describe here. So this consumption Euler equation states that optimal consumption growth of an individual is a function of the interest rate, which is the capital rental rate minus the rate of depreciation, impatience of the household, which is usually denoted by rho, and the coefficient of relative risk aversion, which is theta. If the interest rate is higher than impatience, then the financial market overcompensates for impatience and optimal consumption growth is positive because the numerator is positive. And the coefficient of relative risk aversion mediates this steers this process. So if the risk aversion is lower, then a certain gap between the interest rate and impatience induces a stronger change in consumption, so a steeper consumption profile. So ceteris paribus, if theta is lower and the difference between the interest rate and impatience is positive, then you would get a steeper consumption growth profile. You would get more consumption growth than if theta is higher. Now we need to plug in the capital rental rate to solve for the equilibrium of the model. And for that we can first determine the private rental rate of capital, which is the derivative of the production function of an individual firm J with respect to the use of capital Kj. If we take this derivative, we get that A bar is still in front of the function, alpha comes down from the exponent of capital, and the exponent of capital is reduced by -1. However, we have again to take into account the spillover effect. So A bar is a function of A0 and the aggregate capital stock in the economy, as we had it before in the Frankel version of the model. The aggregate capital stock is again the number of firms multiplied by individual capital because of symmetry, and rational households anticipate this. And now we plug the aggregate capital stock into the spillover specification that we have here, so that we get, instead of this uppercase k, n times lowercase k from here. And then we plug the result into the Euler equation. So this A bar we plug in here, and this result we plug into the Euler equation to get the expression that we have here for aggregate for individual consumption growth. And aggregate output is again given as before, as the number of firms multiplied by individual output. So that's the same expression as we had it in the Frankel version of the model, with A times k to the power of alpha plus eta, and this constant A being determined by an initial level of productivity and the number of firms to the power of 1 minus alpha. Now we can again think what happens in the different cases that we had previously. So if alpha plus eta is smaller than 1, then we would get that k shows up in the denominator here, and the growth rate of the economy would decrease as capital accumulates. So then there would be a steady state solution at which consumption growth becomes 0, as in the Ramsey-Koopmans model if you don't have technological progress, and also as in the solo model without technological progress, and the economy would again converge to this steady state solution. So this first case is very similar to the first case we had in the Frankel version of the model. If alpha plus eta is greater than 1, then we have explosive growth again, because then this increases over time. So the difference between the interest rate and the rate of impatience would increase and be positive and increase, so that the growth rate of consumption would also be increasing. We would have hyper exponential growth, explosive growth, and that's, as I said, not what we can observe in the data, so it's not the relevant case from an empirical perspective. However, there is again case 3 in which alpha plus eta are exactly equal to 1. And in this case, we see from this expression here that kj drops out. We get the expression that we have here for the growth rate of consumption, which is equal to the growth rate of per capita income in the economy. Otherwise, you would not have a balanced growth situation. And this is now equal to a constant here, because A0 is a constant, N is a constant, eta is a constant, and alpha is a constant. And from this, that's the marginal product of capital, you subtract another constant, the depreciation rate and the rate of impatience. So now perpetual growth becomes possible, because this expression here could exceed this expression here, and then you have perpetual growth, because there is no force that would lead the marginal product of capital to decrease. So whenever this is greater than this, it stays so, irrespective of what the level of the capital stock is. So once this exceeds this, we would have perpetual economic growth. Now, ceteris paribus, you see that a higher impatience of households, a higher rho, and a higher risk aversion, higher theta, would both reduce the economic growth rate in such a situation. And finally, one can show that the socially optimal growth rate in such a situation would be higher than the decentralized growth rate, and the reason is just the spillover effect, the externality. Individual firms do not internalize that their production increases productivity at the aggregate level and therefore benefits all other firms. And this externality would ensure that the decentralized growth rate would be lower than the socially optimal growth rate. To summarize, we've now seen the AK growth model, both versions of it, the Frankel model and the Romer model, the Frankel model with exogenous saving, the Romer model with endogenous saving, and both lead to the situation that for certain parameter values you can get perpetual economic growth at a constant rate. And this time, in contrast to the Herod-Doma model, this could be a balanced growth path along which you have full employment. And in addition, you just don't simply assume away the diminishing marginal product with respect to physical capital accumulation. Instead, you assume that there is technological progress driven by learning by doing spillover effects. So the model is, in a certain sense, more credible, but it still does not fit to some of the stylized facts of economic growth, and therefore it did not become so popular over time. Usually it's kind of a shortcut formulation for an endogenous growth model in which technological progress is driven by purposeful investments in research and development, and many of the results that you get in such a model you could also get in an AK growth model, but this is not always the case. And basically the AK growth model was then displaced by the endogenous growth model of Paul-Romer from his famous 1990 paper, Endogenous Technological Change. Thank you very much for watching the video. I hope you found it interesting and useful. For more economic content, please visit my channel that you see on the left-hand side here, or follow one of the closely related videos that you see on the right-hand side.